Uh, Today I want to start with another area, memory organization of computers. But before I do that, I recall that there was something we were discussing in the last lecture of pipelining, which was left undiscussed. Sorry. So we are talking about optimizing programs for pipeline. So we had seen what we could do in hardware to handle pipeline hazards. And then we were looking at some examples of how software could help in this process, which means a compiler could transform a program such that the delays due to pipelining hazards are reduced. So that includes reordering instructions, moving instructions across branches, delayed branches, and predication. So we had seen an example with some of these. So that was an example where we had seen that there were certain number of stalls before we transformed. And then we looked at the areas where delays were occurring, and we actually modified in order to reduce the delays. So the sequence was as follows. We started with a program which would have taken 128 cycles if there were no pipelining stalls, but with pipelining stall, the figure comes to 254. And then with various transformations, we could reduce it to 234, 214, and eventually to 162, which is a substantial reduction. I want to take another example where we would also try to do elimination of branches. Okay, so you have branches at a couple of places. Here you have one conditional branch, then there is unconditional branch, the branch is here, and again there's a call to function, and finally return. So it's a recursive call. Let's not worry about what this function do. You can figure it out. But it will take 16 cycles from beginning to up to this point where you make a recursive call. We are not looking at the whole thing because recursion would mean that depending upon number of time you do recursion, the cycles would change. But from this point to the next call, take 16 cycles. And so here, suppose you don't take any branch. If there were no hazard, these are 16 cycles. But at this point, just 1 minute. So sorry, I'm showing two different situations that if you start do this in first cycle, second cycle, third cycle, if you take branch here, then I'm assuming that there is a delay of 2 cycles. Okay. So instead of this starting in fourth cycle, we are starting in sixth cycle. And then there is a data dependency, so that causes initial delay of 2 cycles. Then again, if you're taking a branch here, there is extra 2 cycle delay adding, and you spend 16 cycles up to this point. Another scenario is that here you are taking a branch here, but at this point you are not taking a branch. So in after 2 cycle of delay, you reach this point, and then you are branching to L3. So in this case, you have taken more branches, and therefore you have reached this point in 18th cycle. Okay, now one way of reducing branches is to use predicated instructions. Okay, instead of branching and doing two different things in two branches, you use that condition to do other operations conditionally. So, for example, here after L1, you're loading something, making comparison, and then on the basis of comparison, you could do a conditional operation. So instead of branching here after this comparison, here you could see that if this is an unsigned comparison, so branch if low to L2, you do this. Otherwise, you branch to L3 and do that. So from L3 onwards is a common, and this L2 is being done only under certain condition. So what we can do is that we make this move operation conditional. So move if low R3 to R0. And now if you see that if this is sequence being followed, at this point there is no hazard coming because of branch, and therefore the number of cycles is reduced. So another replacement for branch is being done here is that here you are doing a comparison and you are saying branch if not equal to L1. Okay, just 1 minute. So in this example, we have, after this comparison, we are doing two conditional operations. One is if it is lower, then you do this. If it is higher or same, then you do that. So this comparison So now you look at these two subtract operations. Here we are subtracting R0 from R1. Okay, and here we are subtracting R1 from R0, right? And these are being done under two branches. If you are in L1, then if this condition is false, you're doing this subtraction. Otherwise, you're doing this subtraction. So a combined way of doing this is, so we are eliminating this branch to L2, and we are doing subtract on low, subtracting R0 from R1, and if higher or same, we are subtracting R1 from R0. Okay, so this branch to L2 is eliminated. Okay, and we have effectively combined these two because what was following these subtractions was a similar piece of code. Okay, and the code after you merge the two branches, you had the same code, making a recursive call to the function and then returning. Okay, so you can see that not only the code length has reduced, the number of delays which come due to branch hazard is also reduced. Okay, Now, this is such a transformation is possible if you have only small pieces of code in different branches. Okay. Uh, if you have, let's say, an if then else statement, and then part and else part have only small bodies, then you could make good use of these conditional or predicated instructions. Otherwise, if you have to put many instructions under such conditions, then there is a uh, you are doing more work than necessary. For example, here, actually you're going through both these instructions. Okay, you are conditionally doing both of these, so the control goes through both instructions are fetched and done. One is effective, one is not effective. All right, so in terms of work done or energy consumed, this might consume more energy. All right, uh, not in this case, but if the number of such instructions were large.
So in the previous slide, why there is a gap between 6 and 9, like a 3 delay of 2 cycles?
Yeah, this is because of data dependency. So unwittingly we have introduced a data dependency here.
But if only one of them will be executed, so
Yeah,
cause
if we can, so there is apparently a data hazard here. We can make our hardware more clever, and if it sees that there is a predicate which is false and therefore write to R1 is not going to take place, then this delay could be avoided in one condition, that this is being, if this first subtraction is being omitted, then the delay may not be there. Okay, but if this is being done, then the processor would actually end up reading R1, and for reading R1, it knows that there is a dependence and it will get delayed. Okay, so under one condition, the delay could be omitted. Under other condition, it will not be, because uh, the way predicated instructions are typically implemented is that you do everything and just stop at the last point where the state change is being made. Right?
oh yes, yes, got it. Thank you.
So next thing being done is that uh, this first subtraction can be moved before the branch. Okay, the reason is that if the comparison says R0, R1 are equal, you're branching to this return point and not doing any of these. But even if the subtract on low is put before branch, uh, if R0 is equal to R1, that condition would be in any case false, and the subtraction would not be done. So therefore, it is safe to move the first subtraction before branch, before this branch is equal to return. Okay, and doing that cuts down on the the two instructions which were apparently dependent. There was data dependency, so they are separated. Okay, and therefore there is uh, reduction in one cycle, which would have been due to out of two cycles which are coming here because of data hazard. You could cut down one. However, there is still between this BEQ and subtract on higher same, I have shown delay of 2 because of this branch hazard. Okay, but on the whole, there is a reduction in the delay. The next thing which is being done here is that uh, this subtract on low is put in the delay slot of this branch. So um, so that cuts on the data hazard. So if you are coming straight, if you're not branching, then there would have been a delay. But because of this movement, the delay is reduced. Okay, now let's get back to this topic of memory organization.
Sir.
Yeah.
So all these things, branch elimination and instruction reordering, this is part of machine-dependent code improvement, right? The last stage of the compiler.
Yeah. So compiler should be aware of these specific machine details, and on that basis, it can perform certain optimization of the kind we have discussed in the examples. So if you look at a complete computer system, uh, processor is just one part, although it is the central part. Processor consisting of arithmetic part and the control part. The other two major subsystems are memory and input output. So now we are going to look at the memory. If you open a server and look at what is the main processor board, you may see a picture like this. This is the Intel Xeon processor, some particular version of that. So this is the slot where you put processor. So processor chip is not there in this diagram right now, but this is where you put processor. The memory is put here in these big connectors. Rest of it is largely pertaining to input output. For example, USB ports, COM port, LAN interface, VGA interface. This is for the display, PCI bus, again USB, SATA. It's a disk interface and so on. So most of it is pertaining to I/O. These are the slots where you put what are called small memory cards. Okay, this DDR4 is one of the memory standards which is used in this one, and there are 4 of these slots. DIMM stands for dual inline memory modules, and if all these are filled up, you can get 64 GB of memory. So what are these DIMM modules? They look something like this. So in this board or in this PC card, it's primarily memory. So you could see that there are 1, 2, 3, 4, 5, 6. There are 18 of identical chips and one 19th chip, which is different. This is the interfacing chip, and these are 18 memory chips on this module. Another identical module is here. So you would wonder why 18? Why not a power of 2 or its multiple? So 18 is because uh, with every 8 bits of with every byte, you could say there is a parity bit for the purpose of error handling. Okay, so therefore it is 8 plus 1, 9 into 2, 18 chips are there. Okay. Have you heard of term core dump? When you are running program, something goes wrong and the system gives a message core dump. So this term core dump comes from one of the earliest memory modules, earliest memory technology is called Faraday core. So dump is nothing but saving complete state of memory, dumping it on some backup store so that you can analyze what happened. Okay. So ferrite core memory was one of the earliest technologies where a small ferrite core. Ferrite is a form of iron which is magnetic, and each core in the form of a ring would contain one bit. So depending upon the orientation of its magnetization, it would represent a 0 or 1. So it's a more dense core memory, and a blow up of this is shown here. You see these are side views of ferrite rings, and these uh, the vertical and horizontal line which you see are the wires running through those. A more conceptual view is like this, that wires are running horizontally, vertically, and also in a zigzag fashion. So X wires and Y wires are to select one of these cores. By passing suitable current, you select, and then if there is a magnetic field in one of these core in the selected core, then you will get a sense signal. So anyway, let's not get into too much of that technology. Idea was just to tell you that this was one of the earliest memory technology. Now, in modern days, you have broadly semiconductor memory, magnetic memory, and optical. So these are three major uh, technological approaches. Among semiconductor memories, you have you use these to form registers, SRAM, DRAM, flash. So by register, I mean typically register file. SRAM and DRAM stand for static RAM and dynamic RAM. RAM is random access memory. And then there is flash memory, which is non-volatile. Uh, Magnetic technology is used in disk drives. FDD stands for floppy disk drive, which is not in use anymore these days. HDD is for hard disk drive. And optical memory is CD, DVD, Blu-ray. These are based on optical technology. So semiconductor memories are random access. That means you can, for example, if you take an array from, let's say, program point of view, you can index into any element of the array. Okay, you don't have to go sequentially. But in hard disk drives, for example, you on a track, you need to go sequentially and reach the point where you want to read. Okay, so there is a bit of sequentiality in the access. You have a combined, you have not entirely sequential access. It's a mixture of random and sequential. For example, on a hard disk drive, moving from track to track is sequential. Moving within a track is sequential, but selection of one of the surfaces, because hard disk drive may have multiple surfaces, and selection of one of the surfaces is random. So you can pick up any surface and do reading writing operation without going through them sequentially. So these different memories vary in their characteristics. Characteristic as in speed, size, and cost. Okay. Typically, there is a trade-off between these. So you have you can create different types of memories. You can have different type of memory modules, uh, ranging from a smallest size to biggest size. The one which is lowest in cost per bit, you can afford a larger size. Okay, and if memory, the technology which gives you higher cost per bit, you can have that small size of that. Also, typically these small memories are fast and bigger memories are slower. So you need to have a judicious use of these. And a way of doing that is to organize these in a hierarchy. You keep the fastest memory, although it may be of small size, close to the CPU so that CPU can access data at a fast speed. But this small memory may not be large enough to hold everything you want. So you need bigger memories. And they could be indirectly connected to CPU, but they provide you the large capacity. So you can have large capacity provided by slow but large memories, and high speed provided by small but faster memories. And the trick lies in arranging these in such a manner that you get the speed of the fastest one and the capacity of the slowest one, almost. Okay. Now, one of the memories, which is somewhere in the middle, is considered as the primary memory. And the one which is lower in the hierarchy is considered secondary memory. And the one between primary memory and CPU is considered cache memory. So I've shown a 3-layer hierarchy, but in general, they could be more levels on either side of primary memory. So primary memory is also called main memory. It's made using DRAM. DRAM gives you reasonable speed and reasonable bulk. So it's somewhere in the middle. Um, it is volatile. That means when you turn off the power, the information is lost. And technologically, it is manufactured on a separate chip. So those DIMM modules which I was showing you, they that forms the memory of the chip. They are separate chips put on separate boards, or could be on the same board but separate chips. And therefore, this is off-chip memory. Cache memory, as I mentioned, there could be multiple levels. There could be 1 to 3 levels, and it is made using SRAM because SRAM is faster compared to DRAM. Are you people aware of the difference between SRAM and DRAM? I believe in logic design course, you would have been exposed to these differences.
Yes, sir. We were briefly introduced to these terms.
Yeah. SRAM is also volatile. Okay. And it is integrated on the same chip as the processor. So cache is typically, with the present technology, cache is on the same chip as the processor. But in earlier days, the cache also was on separate chips. Now, one or more levels of cache could be integrated on the chip itself. So in a typical organization where you have, let's say, 3 levels of cache, L1, L2, L3, there would be some characteristics which would differ from the point of view of whether instruction and data are separate or not. So in L1, typically, there are 2 separate L1 caches, one for data, one for instruction. So it's called split cache. But subsequent levels L2, L3 would be unified. That means same cache holds data as well as instruction. Now let me relate this issue of splitting L1 into data and instruction. Recall that in single cycle design, we had separate data instruction memory. In multi-cycle design, we combined. And in pipeline, we again split that. The idea was to make sure that there is no resource hazard by keeping the 2 parts in the same memory. Okay, because an instruction may need to make a reference. All instructions make reference to instructions. They access memory for getting instruction, and some instructions, that is load and store instruction, would make another access to memory for data. So if you have combined cache, if you have unified cache and have a pipeline design, then that would cause a structural hazard. So therefore, uh, at L1, from where you are immediately getting instruction data, you keep the cache as split. The technical name for an architecture where you have separate data instruction cache or instruction memory and data memory separate is a Harvard architecture. Okay. Okay. The second characteristics on which these levels would differ is in terms of how multiple processors which are on the same chip. So you talk of 8-core, 4-core processors. So how those processors access or share cache. So L1 is invariably private. That means if you have 4 cores, each of those processors will have separate L1 cache. Whereas L3 is always shared. That means there's a common L3 for all cores. L2 could be either way, and there are examples of both. So to get an idea of sizes of these, let's look at a processor, an Intel Xeon E7-8870, where level 1 cache is of size 64 kilobytes, split between instruction and data. Level 2 cache is 256 kilobytes. It's a unified cache. And these are private. Okay, so these are exclusive for each processor, each core. And level 3 cache is of much larger size. It is shared by 10 cores. Okay, so you get idea of the sizes. And external address space, which could be used to access the main memory, is 16 terabytes. Okay, so every system may not have that much of memory, but that is the address space. That means uh, if you take log of this number to the base 2, you will get how many address lines are there, how many bits are there in the address. Okay, now come to secondary memory. Uh, so this could be flash or disk drive. So you often see SSD, solid state drive, or HDD, hard disk drive. So solid SDD is semiconductor memory or solid state memory, and HDD is magnetic. These are not purely random access. There's a mixture of random and sequential, and these are non-volatile. That means even if you turn off the power, the information is retained. So these connect to the processor more like an IO device or peripheral device. Okay, so reading and writing into these is more like performing input-output. The backup memory is used for archival, and you have optical disk, hard disk drive. You could back up in a cloud. These are external and removable. Okay. Now let's see how a processor would make an access to memory when there is a hierarchy. So I'm showing 2 levels to illustrate the concept. So this box is processor. This is one faster memory, let's say cache, and this is main memory. Okay. So processor wants to make an access to some address of memory. It will check if that information exists within this faster memory. Okay. So if the information exists, then we say that there is a hit. Otherwise, if the information is not there, we say it is a miss. And in that case, we need to go to the next level of memory. and we will find it. If there are only two levels, you will of course find it at the next level, but otherwise same process could be repeated at the next level also. And the data transfer would be involved. The data comes from slower memory to faster memory, and from there CPU can take it. So between cache and main memory, the unit of transfer is called a block. So it's not one byte a word, but you would typically transfer more data for future reference, and that is a block. So why does the hierarchy work? I mean, you might say that, okay, uh, eventually you have to go down to the slower memory. So that will dictate the speed or will make the whole thing slow. But the hierarchy works because of locality. Locality is of two kinds: temporal locality and spatial locality. Locality of space and locality of time. Uh, Temporal locality means that if you make reference to some data or some instruction, there is a likelihood of repeated references to the same thing over time. For example, uh, you have a small loop in the program, and the instructions which are there in the loop body will be repeatedly accessed, depending upon how many times the loop iterates. And similarly, uh, it is likely that there are many access to the same data. So there is temporal locality both in data and instruction. For instruction, it is fairly obvious that loops will give you temporal locality. Spatial locality means that reference to uh, location which are nearby in space. Space here means the address space. So if you are referring to some element of an array, you're likely to refer to elements of the array adjoining that. So in memory address space, you are likely to make references to data which are close by in addresses. And that happens in instruction also. Even when you have branches in the program. So if there are no branches and you're going sequentially, there is clearly spatial locality. Okay. But even if you have branches, most of branches are going to some nearby addresses. Okay. You don't branch very far. Uh, More likely to branch close by. So we can exploit these to make sure that most of the time you are able to get the information you want in the faster memory. A special case of um, the spatial locality is sequential locality. Okay. In general, spatial locality means that you are making accesses at the nearby addresses. Sequential locality means that you are going in the order in a particular sequence. So let us see how it works out through a small example. So I'm showing a cache which has 8 words. Okay, these are labeled as 0000 to 111. And we have memory which is 4 times in size. So what could this word of cache contain? We could arrange so that can it can hold or it can house any of these 4 words which have uh, 001 as the last 3 bits of address. So in memory, which is of much larger size, if you look at various addresses, those addresses which have the rightmost 3 bits as 001, they can be associated with this particular word. And similar thing is for all the words. Okay. So now suppose you want to access this particular word of memory, you know where it can possibly be. It may be there, may not be there, but if it is there in the cache, it has a fixed location where it can be. So all these words in a way map to one particular word of cache. And same thing will you pick up another word in the cache, and their corresponding words in main memory, which will map to this. Right? So what you need to do is you need to look at rightmost few bits of the memory address and check in the cache if that word is there or not. So cache access mechanism is something like this. I'm showing now a cache of size 4095 words. Okay, 4096 words, 0 to 4095, 4K words, and a 12-bit field in the address. So I'm not taking rightmost 12 bits. I'm leaving out 2 bits here uh, to decide one of the bytes in the word. So since these are byte addresses, I'm leaving out the right 2 bits, which will correspond to byte location within a word. So apart from that, I'm taking rightmost 12 bits to decide where I go in the cache. Okay, so use this as an index into the cache, and there I need to, how do I check whether the actual word I'm looking for is here or something else is there, because uh, all addresses which have same 12 bits here will map to this. So I need to keep what is called a tag with the cache words. Okay, this tag will tell you which of the various possible main memory words are sitting in this location. Okay, uh, and how big this tag has to be? This is exactly same as the remaining bits of the address. Okay, so I can compare the remaining bits of the address with the tag and check if the word I'm looking for is there or not. So here I'm showing one more field in each cache word. So let's say this is 32 bits. So there are 32 bits of data, and 32 minus 12 minus 2, which is 18 bits of tag and 1 bit which is valid bit. Initially, the cache may be empty, so you can mark everything as invalid. And as information is brought into the cache from main memory, the valid bits are made 1. Okay, so now the process is like this, that when you want to make an access, you take these 12 bits from the address, index into the cache. There, first you look at the tag, first you look at the valid part. Okay. If valid bit is 1, then check if tag matches this. If that happens, then this data is what you're looking for. Otherwise, you need to access the next level of memory. So conceptually, I'm showing a match occurring. So there is a comparator which looks at the tag and this field of the address, 18 bits. And if there's a match here and valid bit is 1, then I declare it as a hit. And if there is a hit, then I read out this data. Okay, I'm showing this for reading from memory. Writing is similar. So in case of writing, if there is a hit, I write the data. So just the direction of transfer differs. Is there any question at this stage? How cache works?
Sir, if there is not a hit, then would we also maybe change the tag and also the data in the writing?
I missed the initial part of your question.
If in writing there is not a hit, would we also change the tag as well as the data?
Okay, so there are some issues with that. We'll discuss that in detail at the moment. So at the moment, let's assume that if there is a hit, we write the data. If there is miss, then we'll have to figure out what to do. Yeah, there was one more question. Somebody else was trying to speak. Yeah. Can you be a bit louder? I'm not able to hear you.
Why do we need the valid bit?
Sorry, your voice is getting cut. So try once more. I think we have lost the voice of whosoever was asking question.
Hello, am I audible?
Yeah, I can hear you. Yeah.
Sir, why do we need the valid bit exactly? Like
Okay.
just to check whether it contains something or there's some other
Yeah.
application.
So assume that initially, you see, suppose you start computer refresh, start running a program. Your entire information is in main memory. Cache has nothing. So how do we indicate that situation when there is something in the cache? So initially we mark all these valid bits as 0. As and when something gets filled up in cache as a result of miss. So when a miss occurs, for the moment assume that when a miss occurs, you get information into the cache from next level and then proceed the same way. Okay. So when you bring something into the cache, then you mark it as valid. So
Okay, so when V is marked, let's say 0, let's say we indicate that it's not valid. So
yeah,
even then, cache may contain some garbage, right? It might
yeah,
not contain.
garbage tag field will have some garbage. So
Okay, okay.
you should not interpret this as valid data.
Oh, okay. Thank you,
So
sir.
this is for that purpose. Sorry. Okay. To exploit spatial locality, what we do is we make cache word. We create cache blocks. Okay. In the sense that you move data in larger chunks rather than one word or one byte. Okay. So here I'm illustrating a cache block of size 4 words. You see this entire horizontal row indicates one cache block where these 4 parts which are shown, these are 4 words. So these 4 words have a common tag and a common valid bit. Now what I need to do is that if I'm able to locate a valid block which is matching in terms of address, I would need to access the word within the block and byte within the word. So I have 2 bits to select a byte within a word, another 2 bits to select a word within a block. This is called block offset. That means where the word is within the block. And instead of 12 bits here, I have only 10 bits which index into an array of size 1024. So keeping the total cache size same, this was the previous picture, 4K words. Those 4K words I have organized as 1K blocks, okay, or 1024 blocks. So the additional thing which is required here is that I have to select one of the words. I'm having a multiplexer for that, which is controlled by the 2 bits coming from this particular field. Okay, and once I have a word, I can again select depending upon what instruction it is. If it needs whole word, it's fine. If it needs a byte or half word, then I'll take part of it. So rest of it is same. Uh, how would the performance vary as you vary the block size? So now with a block, we are trying to capture the spatial locality. That means if you suppose there is a miss for certain address, then instead of getting just one word, we are getting one whole block with the hope that you are likely to access other words within the same block in very near future because of spatial locality. Okay, so the question is how big we should have this. One might imagine that larger the block is, better exploitation of spatial locality will happen and you will have better performance. So performance is being shown here in terms of what is called miss rate. That means what is the percentage of the time you have a miss when you make an access to memory, and what is the percentage of time you have a hit. Okay, so suppose 1 in every 10 accesses is a miss, then miss rate is 10%. So you can talk of miss rate as a fraction or as a percentage. And this shows how typically the miss rate would vary as you increase the block size. So block size is being shown as horizontal axis, 4 bytes, 16 bytes, 64 bytes, and so on. And you could see miss rate dropping, but at some point there may be a case of diminishing return. Okay, you could see, for example, it is most prominently seen in the top curve, which corresponds to a small cache, that if you make blocks too large, then you end up in having too few blocks. Okay, so for example, uh, if cache is just 1 kilobytes and you are trying to make 256 blocks, 256 byte blocks, then they are just 4 blocks. Okay, and you're more likely to be shuttling between blocks and having a high miss rate. Okay, so beyond certain point, you start getting reduced performance. So one way of putting this is that a block captures a spatial locality, and the number of blocks you can house in the cache uh, tells you how many localities you are able to capture. So let's say you have 16 byte blocks, and the cache can accommodate 1,000 of those. Suppose you have 16 KB cache and block size is 16 bytes. Okay, that means at any time cache can accommodate 1,000 blocks, and those 1,000 could be scattered anywhere you want, and therefore you are able to capture the locality as at 1,000 different places. But when the number of blocks is too few, then you are able to capture locality at very few places. Okay? And a program, for example, may be requiring locality at multiple places. You know, you may be shuttling between several loops. Okay, so you may execute one loop here, then move to some other place, execute a loop there, move to another place, execute a loop there, and the process may repeat. So there are many localities to be captured. One more thing you can observe from this chart is that as cache size reduces, the miss rate goes higher. So the lowest curve is corresponding to the largest cache, and as the cache size reduces, you have higher and higher miss rate. Okay, so miss rates like 40% or 20% are pretty bad. You want in real practice you will like to have 1% or maybe just a few percentages. Okay, now we took an approach where we said that for every memory location, for every memory address, there is a fixed point in the cache. Okay, such an arrangement is called direct map cache. So given an address, you know where it can exist. Opposite to that is an associative cache, where given data could be placed anywhere in the cache. Okay, so you have a block in the memory instead of being confined to one particular location. In cache, you can place wherever you have space. Okay, you can place it anywhere. That gives you much more flexibility. But consequence of that is that you need to look for, in the first case, you took one field of the address and you could directly index into the cache and get to the location where you check for presence or absence, hit or a miss. But in case you need to look at all over the place, okay, and if you start doing that sequentially, then the whole purpose of having a cache would be lost. So you need to actually look for all places at the same time concurrently. In one go, you want to check all of the places, and that's where the term associative comes, because it's like associative memory, where you you specify the tag value and see if that tag exists anywhere. Okay, so the cache block could be present anywhere, and you need to locate it by its tag. So you compare tag values at all the places, and if a match occurs, that means the data is present. Now, comparing tag everywhere would be very expensive. So practically what you have is called set associative cache, which is something in between. Instead of making it completely free, allowing any cache block to exist anywhere, you restrict the location. So you divide cache into what are called sets. So these sets are groups of locations in the cache where a block could exist. So in this example, I'm showing that this cache has space for 8 blocks. You divide this into 4 sets. Then a given block could exist anywhere in the associated set. So for a given address, the set number is fixed. Okay, you can index into a set. You can reach a set by indexing, and within a set you need to do parallel comparison of the tags. So in this case, you would need a comparison at 2 places. So this is a conceptual view of a set associative cache, which is 4-way. 4-way means that set size is 4. Okay. So for the same capacity, now I have 256 rows. Okay, I've made it 1/4 further. So the total capacity is 4K bytes, right? 4K. Sorry, it was 4K words. Yeah. So as usual, you have 2 bytes, two bits which give you byte offset, 2 bits which give you block offset, and now instead of 10 bits for index, I'm having 8 bits for index. Okay, because I need to go to one of the 256 rows. This can be selected by 8 bits, and within each row, I have 4 tags. Okay, 4 blocks, each with its own tag and valid bit. So there are 4 comparators. One is here, one is there, one is there, and so on. 4 comparators which are comparing the tag in parallel. And this comparison decision conjuncted with the valid bit indicates hit. So if either all 4 will say that there is no match, okay, or one of them will say that there is a hit. So we have an OR gate here. And output of this is 1 if there is a hit, otherwise there is a miss. Each of these is 1 block. So 1 block means 4 words or 128 bits. I'm showing the width of this as 128 bits. Out of these 128 bits, we select 32 bits or 1 word by using this, what I called as block offset. one of these four may be selected if there is a hit. Okay, so the outcome of these comparisons, tag comparison and conjunction with valid bits, we are using these to control this mux, which will select one of these. Okay, so if there is a hit, you will get one word of data. Now, yeah.
Sir,
Yeah.
like where does the selected for the below, like that one, fifth mux come from?
Oh, why is this lower marks coming from?
Yeah, selected of this one.
Yeah, so see, each we don't know where the hit is. Okay, these are four blocks which are forming a set. So this is a selected set based on these index bits, index field, and either all four will say miss, or at most one will say a hit, and three will say a miss. So out of these four groups of 32 bits, one has to be selected in case there is a hit. So I'm having, rather than two encoded lines for selection, I'm having four decoded lines. So each line would enable output of these multiplexer, and the result will be placed here.
So like this is a combination circuit. So in case there is no hit, then what will the data be? Will it be zero?
This would be zero, yeah.
Okay, okay.
Or it could be anything. I mean, it's don't care if there is no hit, but typically it will be zero. So this arrangement of multiplexer could be modified differently. Could be so you could actually have this multiplexer, the lower multiplexer, coming first. Okay, you could before you select a word out of a block, you could first ensure if there is a hit or not. So you select one of these four groups of 128 bits based on the these potential hit lines. And if there is a hit, then you select one word out of these 128 bits. So these two approaches are called early select or late select. Early select means that you access data while tag matching is going on. Sorry, early select means that you what I'm showing here is actually a late select, where you while tag matching is going on, this is being done. You know, this first multiplexing is being done. Sorry, I lost the laser pointer. Yeah. So in this diagram, the first level of multiplexing is happening concurrently with tag matching. Well, this entire thing is combinational, but in terms of propagation delay, while this comparison is happening, this multiplexing is happening. Okay, and once stack matching has been done, then you are making this multiplexer active. If you put this multiplexing before, then the second multiplexing has to wait till the tag matching happens and this bigger multiplexing is done. That will cause a bigger delay as compared to what is shown here. Okay, now let's get idea of the sizes and bits in various fields. Suppose you have main memory, which is capital M bytes or 2 raised power small m bytes. Okay, and cache size is capital S or 2 raised power S. Block size is capital B or 2 raised power small b. So number of cache blocks is the ratio of S and B, or 2 raised power S minus B. Number of possible tag values equal to number of memory blocks that map to the same cache block. Okay, and that gives the number of tag bits as m minus s. So number of memory blocks that map to same cache block is m by s or 2 raised power m minus s, and number of tag bits per block is m minus small m minus small s. So in a direct map cache, if you have m bits as the total number of address bits, out of which tag bits are m minus s and index bits are s. Out of these s bits, actually, you have b bits to access a byte within a word. So sorry, to access a byte within a block. Okay, so we had two bits to access a byte within a word and 2 bits to access word within a block in that example. So for that example, the small b would have been 4. And number of index bits actually is s minus b. So in that example, this was we had, how many we had? We had 18. Sorry, we had 18 bits for tag, 10 bits for index. We had 18 bits here, 10 bits here, and 4 bits here. So total making up 32 bits. In a set associative cache, the index size will reduce because we have less number of rows, and you have more tag bits. Degree of associativity, suppose that is A, capital A, or 2 raised power A. The example we had shown, this capital A was 4. So the number of sets equal to cache size divided by block size multiplied by the degree of set associatability. Okay. So the index bits are required to select one of the sets. So it is log of 2 to the base, log of s by ab to the base 2, or which is small s minus small a minus small b. Okay. So index bits are reduced by this amount a, and number of possible tag values equal to number of memory blocks that map to the same cache set. This is larger m by s into a, and therefore the tag size is m minus s plus a. In some sense, one might say that the tag bits are kind of overhead. Okay, the actual useful data is there in the blocks, but tag bits are overhead to make the cache work, and that overhead is the total number of tag bits, which is m minus s plus a into, this is size of each tag multiplied by the number of blocks. Okay, so that's the overhead in terms of tag bits. And in terms of similar picture, the index is reduced to S minus B minus A, and tag has increased to M minus S plus A. So we have looked at a simple principle of how cache operates. There are a lot of other issues, other techniques, which are actually captured in terms of cache policies. So there are cache policies related to placement, reading, loading, replacement, various actions associated with cache operation. And different choice of policies give you different cost, performance, other parameters. So we have talked of already placement policy, which memory block can get placed where, and we had three options: direct map, fully associative, and set associative. The read policy refers to when we perform read and from where do we read. So there are variations when we answer this question, and we'll talk of that. Loading, how do we fill the cache block, the order in which bytes or words get filled. When we need to bring a new block, which is the old block from the cache which needs to be thrown away or needs to be replaced. Fetch policy answers the question of when to fetch a new block. Write policy talks of when to write and where to write. Okay. So let's look at some of these. When to initiate memory access. So it could be sequential. That means initiate memory access only after detecting a miss. Or it could be concurrent. Initiate memory access along with cache access in anticipation of a miss. So simple approach is to hope that things you're looking for are in cache. Only if there is a miss, then you worry about looking at the memory. But a little aggressive approach is to start looking at memory at the same time. Okay, so that would save some time. But in case there is a hit, then that's a wasted effort which can be abundant. So you can, when there is a miss, then you will save some time. Where CPU gets data from. So there are two options: without data forwarding. So the data forwarding is coming here in a slightly different context. So suppose there is a miss. Then one approach could be that you first fill the missing block in the cache and then pass on, then allow CPU to read from the cache. The other approach is that forward data to CPU as it gets filled in cache. So again, this could potentially save some time. What should be the order of bytes or words as you're filling in a block of cache? The block in cache may be loaded starting from the missing word in a wraparound manner. Okay, so suppose you have block of size 16 words. Okay, and there is an instruction which is trying to access the sixth word. So now there is a miss in the block, miss for this particular block. What you could do is you could first get this. The intention is to get the entire block, but first get the sixth word because that's what you want urgently, immediately. So get the sixth word, then seventh, eighth, and so on. And after 16th word, you start with first and so on. So in a wraparound manner, you could fill up the block starting at the appropriate point. And this is useful when data is forwarded to CPU as it gets filled in the cache. Otherwise, if you are giving it to CPU after filling the entire block, then it doesn't make sense. One very important question is that since cache has limited capacity, once cache is full, once all valid bits have turned into 1, you get a new block, you have to displace something. You have to replace something. So which one to replace? There are many options people have tried. One is least recently used. That means you keep track of which has been recently used. It is likely to be used again, so don't throw it away. Pick up something which was least recently used, which was used farthest away in the past. The next is least frequently used. So one which is commonly, repeatedly being used, you leave that. One which is getting used less often, you throw that. Another simple to implement is first in, first out. So the existing blocks in the cache came in certain order. The one which came earliest, you throw away that one. Or last is random. Then don't apply any of these logics. Just pick up one randomly and do it. Practically, it is found that the first one works best. Okay. Ideal thing would be to predict the future references, and the one which is to be used farthest away in future, that should be thrown. Okay, but that would mean a lot of prediction. And what is most easily implemented is LRU, or least recently used, and which works fairly well. Okay, so just to capture what I've discussed, we have talked of placement policy, direct, associative, set associative. We talked about read policies, sequential read, concurrent read, and with or without forwarding. Load policies, with or without wraparound. Replacement policies, LRU, LFU, FIFO, and random. Two more things we need to talk of are fetch policies and write policies. So we can look at fetch policy. You have the normal thing is demand, what is called demand fetching, that you fetch a block when there is a miss. Okay. The other one is prefetch. You fetch in anticipation. Prefetch can be done with the help of hardware, or it could be software-driven prefetch. Okay, hardware-driven prefetch is usually very simple-minded. That you are fetching a block in anticipation. You fetch the one following it also. Okay, in the address space, the one which is after this block, you fetch that also. Software-driven prefetching means that compiler introduces prefetch instructions. These are special instructions which allow a block to be prefetched from the cache. Okay, so program has to analyze where, for example, a load instruction is coming, and suitable number of steps before that, it could put a prefetch instruction, so that by the time you reach that load point, the block which was required is already prefetched. Now they could be, when you do a prefetch, you could incur wastage. So it's not, it doesn't come free. If prefetch has gone wrong, that means you get something but don't end up using it, then it's a wasted effort, and you may have displaced something useful from the cache, because cache has always a limited space. Okay, so for example, that you suppose you do software-driven prefetch. So there is a point in the program where some address, some load is to be performed, and some instruction before that you have done prefetch. Now between these 2 points, there could be a branch, and that branch could take you away from that load. Therefore, this prefetch which you have done could be wasted. Okay, so one has to be careful and uh, cannot keep doing this arbitrarily. Okay. Um, Lastly, quickly about write policies. When there is a write hit, then obviously you can write in the cache. So there is that's straightforward. But should you also write in the memory? Both ways are possible. Writing into memory has an overhead because writing to any reading or writing from memory takes time. But it will keep the two consistent. Okay. If you're writing in cache and memory both, you are ensuring that the copies in cache and memory are always consistent. If you're not writing, then you need to deal with this inconsistency. Okay, so cache has the latest data, main memory has the stale or old data. Before we look at that, let's see what could happen when there is a write miss. Should you write in cache or should you write in memory or both? In cache, maybe. In main memory, definitely yes, if the answer to the above is no. If you're writing in cache, you can skip writing into memory, but if you're not writing in cache, you must write in memory. So somewhere you have to write. Um, if you're writing in cache, where to write? If you are writing in memory, then you have to worry about the overhead. But writing in memory, as in the previous case, will keep the two consistent. And if not, we have to deal with the inconsistent data. Okay, I'll stop at this point. Yeah, question?
So when we write in cache,
Yeah.
then this should be stored in memory at some time, right? Because cache is volatile.
Yeah.
So this won't be permanent. How do we do that?
Okay. Well, for that matter, even main memory is volatile. So that is not the question, but sometime you have to make them consistent. You can't keep them inconsistent all the time. So let's get back to this cache hit scenario. So suppose we write in cache, but we don't write in memory. Now a time would come when this cache block where you had written is getting displaced because of something else coming in. So at that time, you need to update the memory, and that is called write back. So you need to do write back before you lose the data. That's the important thing. Otherwise, you have updated the cache. If a read comes, you can read from the cache itself. So cache will have the latest data always, but main memory need to be made consistent when the cache is about to lose those changes which were done. Okay, when those writing which were done in the cache, that needs to be preserved in main memory before it gets lost from the cache. Okay, we'll stop at this point.
So sir, one more small thing.
Yeah.
When we allocate space for something that using in C we have malloc thing. So
Yeah.
we do that in a cache or memory?
Memory.
It is done in memory.
Yeah, ideally, ideally the programmer should be unaware of the cache. Okay, programmer should see what is the main memory or primary memory. That's a picture the programmer must have. So cache works completely automatically. Okay, leave aside software-driven prefetch and stuff like that. In its purest form, cache is completely transparent to the programmer. Okay, it should only appear as a device which is only increasing your speed or performance. So when you do malloc or in any memory allocation, it is in the main memory space. And as you try to read and write from there, things will come into the cache.
Okay.
So actually, there is a catch in what I have said. Typically, it will not be even main memory. It will be what is called virtual memory, which we will discuss in one of the subsequent lectures. So for the present discussion, assume that all this is happening in the main memory, and as and when required, things are brought into cache. Any other question? Okay, thank you.